There are questions so large that even asking them feels dangerous. Questions that quietly expose how small we really are. And one of the biggest is this: are we alone in the Milky Way? Not in the universe, not in some vague philosophical sense, right here in our own galaxy, among its staggering number of stars, planets, moons, and silent distances. Could there be another civilization somewhere out there, looking up, building machines, sending signals, and wondering the exact same thing? At first, this sounds like science fiction, a late-night thought, the kind of idea people throw around because the night sky makes human beings feel poetic. But then, science did something interesting. Instead of treating the question like fantasy, it tried to organize it. That is where the Drake equation comes in. The Drake equation is not a machine that spits out the correct number of aliens hiding in the galaxy. It is not a magic cosmic calculator. It is better understood as a scientific framework, a way to take an enormous question and break it into smaller questions that scientists can actually think about. Frank Drake proposed it in 1961 as a way to estimate how many communicating civilizations might exist in the Milky Way. That phrase matters: communicating civilizations. Not just life, not just bacteria, not just strange microbes under alien ice. The equation is aimed at civilizations advanced enough to release signals or technology that in principle could be detected across interstellar space. And that immediately changes the game. Because finding life and finding intelligent technological life are not the same thing at all. Earth had life for billions of years before anything resembling radio showed up. So the Drake equation is not merely asking whether life exists somewhere else. It is asking how often the entire long chain succeeds. Stars form, planets form, some worlds become suitable, life appears, intelligence evolves, technology emerges, and that technological phase lasts long enough for another civilization to notice. When you hear it laid out that way, the equation feels less like one formula and more like a gauntlet. The first part asks how often stars form in the galaxy. That matters because more stars mean more chances for planets and more chances for life-friendly conditions. Then comes the fraction of those stars that have planets. Decades ago, that number was deeply uncertain. Today, astronomy has changed the conversation dramatically. We now know that planets are common, not rare decorations scattered across the galaxy. But quantity is not enough. A galaxy full of planets is not the same as a galaxy full of living worlds. So the equation asks another question: how many of those planets might be capable of supporting life? This is where ideas like the habitable zone come in. It's the region around a star where conditions may be right for liquid water to exist on a planet's surface. And liquid water matters because on Earth, water is one of the key ingredients tied to life as we know it. That doesn't prove every planet in a habitable zone is alive. Far from it. But it gives science a place to start. And here's where the mystery gets delicious. Astronomy has gotten much better at the early parts of the equation. We know stars are everywhere. We know planets are everywhere too. We can identify some planets in habitable zones. We can study atmospheres, temperatures, orbits, and host stars. In other words, the front half of the Drake equation used to be a wall of guesswork. Now, parts of it are slowly turning into measured science. But the back half remains brutally uncertain. How often does life actually begin, even when conditions seem favorable? We don't know. On Earth, life appears to have arisen relatively early in the planet's history, which tempts some scientists and thinkers to say maybe life starts easily when the conditions are right. But Earth is still a sample size of one planet, one success story. That's scientifically frustrating because you can't build a universal law from a single example without risking self-deception. Then comes the next leap. How often does life become intelligent? Again, Earth gives a strange answer. Life stayed simple for a very long time. Intelligence, at least the kind that builds telescopes and argues on the internet, does not appear to be the automatic destiny of biology. It may be common, it may be absurdly rare. We don't know. Then it gets even harsher. Even if intelligent life appears, how often does it develop technology capable of interstellar detection? Intelligence alone is not the whole story. Civilization has to take a particular path. It has to turn thought into tools, engineering, and signals. And then comes perhaps the most brutal term in the whole equation. How long does such a civilization remain detectable? This is where the Drake equation stops feeling like a hopeful search tool and starts sounding like a mirror held up to humanity. Because even if intelligent civilizations arise many times in the galaxy, if their signal-emitting technological phase is brief, then the odds of two civilizations overlapping in time may be painfully low. A culture might exist for thousands, millions, or billions of years, but only spend a tiny slice of that time blasting detectable signals into space. Or it might destroy itself, or go quiet, or switch to technologies we don't know how to detect. That last factor is one reason the equation remains so haunting. It doesn't only ask how often civilizations begin, it asks how long they last. In that sense, the Drake equation is not just about aliens. It's also about us, about the survival of intelligence, about whether technological societies tend to burn out, grow up, hide, or endure. The equation turns extraterrestrial life into a question about astronomy, biology, evolution, engineering, and civilization, all at once. And that is why the Drake equation has survived for so long in scientific culture, not because it gives a final answer, but because it organizes ignorance beautifully. It tells us where our knowledge is strong and where it falls apart. We are better than before at estimating how many stars there are, how often planets form, and how common planetary systems may be. We are better at finding exoplanets than any previous generation of humans could have imagined. We have moved from knowing almost nothing about worlds beyond our solar system to confirming thousands of them. That alone is a stunning shift in perspective. The sky is no longer a field of isolated suns. It is a crowded architecture of worlds. But when it comes to life, intelligence, technology, and longevity, we are still standing in fog. And that fog leads naturally to another famous idea, the Fermi paradox. If the galaxy may contain so many stars and planets, and if some reasonable versions of the Drake equation produce non-zero numbers of civilizations, then where is everybody? Why have we not seen a probe, a megastructure, a signal, a clear artificial beacon? Why does the universe look so silent? Maybe civilizations are rare. Maybe intelligent life is common, but technological life is rare. Maybe civilizations usually destroy themselves. Maybe interstellar travel is too hard. Maybe the galaxy is full of quiet observers. Maybe the signals are there and we are still too primitive to recognize them. Maybe the silence means something grim. Or maybe it only means we have barely started listening. That last point matters more than most people realize. Humanity's serious technological search for extraterrestrial signals is incredibly young. Compared with the age of the galaxy, our listening effort is practically nothing. We are beginners, walking into a vast library, glancing at one shelf for a few seconds, then asking why we have not read all the books yet. The silence may be real, but it may also reflect how little of the search space we have actually explored. So the real power of the Drake equation is not that it tells us a number and ends the story. Its power is that it tells us where to keep looking, what questions matter, and why the search for life is no longer just philosophy. It is a scientific frontier. It turns the biggest question in the night sky into a map of smaller questions. How many stars are born in the galaxy? How many of those stars have planets? How many of those planets might support life? How often does life actually begin? How often does intelligence appear? How often does intelligence build detectable technology? And how long does that detectable phase last? Every term is a door. Some doors are opening because astronomy is improving. Others remain locked because biology beyond Earth is still unknown. That is what makes this whole story so thrilling. We are living in the moment when one half of the equation is becoming data, while the other half remains one of the deepest mysteries in science. So, are we alone? The honest answer is still the most uncomfortable one. We do not know. But now the question is no longer just a philosophical whisper. It is something science can attack, piece by piece, world by world, signal by signal. And that may be the most astonishing part of all. Humanity has reached the point where we are no longer only staring at the stars and wondering, we are starting to build methods for measuring the odds that someone else is staring back. That changes everything. Because once you stop treating the search for alien life as fantasy and start treating it as a measurable scientific problem, the universe feels different. The stars stop looking like distant lights and start looking like possible addresses. The silence stops sounding empty and starts sounding unfinished. The question stops being childish and becomes one of the deepest investigations our species has ever attempted. And maybe that is the true power of the so-called alien hunting equation. It doesn't promise answers. It gives us a structure for asking better questions. It reminds us that science is not only about certainty. Sometimes science is about building a ladder into the unknown and climbing anyway. So, the next time you look up at the Milky Way, remember this. Somewhere in that river of stars may be worlds with oceans, skies, storms, chemistry, biology, and history. Somewhere out there, life may have begun. Somewhere, intelligence may have risen. Somewhere, a civilization may have built its own version of mathematics and asked its own version of the same terrifying question. Are we alone? And maybe, right now, they are listening too. Do you think the silence of the galaxy means no one is out there, or only that we have barely begun the search? Tell me in the comments. And if you enjoy deep space mysteries explained in a clear, cinematic way, like, share, and follow WiseUse for more.